Hello, my name is Justin Chow, and I am a senior design student, and I'm in a senior design team with Jesse Dangle and Matt Mutarelli. Our senior design team project was to design a data acquisition system. A data acquisition system measures physical signals and then displays them digitally on a computer screen. Our data acquisition system will only measure voltage signals, and so in essence will work similar to an oscilloscope. So as you can see here from our oscilloscope is going to be powered by plus or minus 12 volts, as seen right here, and it will have probes just like a regular oscilloscope. Right now I'm showing two probes right here. Here's probe 1, and here's probe 2. They're both exactly the same. So inside the probe, at the front of the probe, there's this chain of resistors. And this chain of resistors creates a voltage divider that will divide the voltage measured at the probe by a different ratio. So this top level right here will divide the input voltage by 5. This divider right here will divide the input voltage by 10, and this voltage divider here will divide the voltage by 20. And as you can see, the total resistance of this resistor chain will be the input resistance of the probe. Most standard oscilloscopes on the market have an input resistance of about 1 mega ohm. As you can see here, ours is only 100K plus these resistors, so it's less than 200K. So in terms of input resistance, it's not very high, which can be potentially dangerous because if the input resistance of the probe is not large enough, it may affect the circuit that it's measuring. Inside the probe, there's also this buffer and this low-pass filter cascaded together multiple times. Now there's 3 of these low-pass filters cascaded to create a third-order low-pass filter. And this low-pass filter is meant to be used as an anti-aliasing filter. What we mean by an anti-alias filter is it's supposed to filter out frequencies that the system cannot handle. So our oscilloscope system can handle frequencies up to 1 megahertz. So these low-pass filters will filter out signals higher than 1 megahertz and attenuate them to 0, so that way they don't mess up the system. And they're cascaded with buffers in between to isolate each filter. So now that we've taken a look at the probes, let's actually use them in action. And so here I have a circuit. And this is a full wave rectifier with 2 pairs of diodes in either direction across a resistor. Now in order to measure the voltage across this resistor, I'm going to need 2 probes because these probes are not differential probes and must be grounded. So I have one probe on one end of the resistor and another probe at the other end of the resistor. And I can find the voltage across this resistor by subtracting one probe from the other probe. So with these 2 probes, this little junction here and this text will link this spot to this part of the circuit for this probe, and this will link this to the other probe. So now we're going to test this full wave rectifier on a signal. So for our first signal, let's consider a triangle wave. And let's say its amplitude voltage is 20 and its frequency is 5 kilohertz. So now I'm going to run a simulation using that. So for our simulation, for a transient analysis, I need a certain amount of time to run this for. So I'm going to run this for 1 millisecond. That'll give me 5 oscillations from a 5 kilohertz signal. So I click that and I run that, and it might take a bit of time for the simulation to run because, as you can see, even just one individual probe has 3 different voltage dividers, and each divider has 3 low-pass filters cascaded on top of each other. So it might take a while for the program to develop a simulation solution for that. But eventually it'll get around to there. Okay, and this is our simulation output for 1 millisecond. So right now, all the outputs of the probes are laid out on top of each other. So in order to see each individual one, I'm going to separate the curves right here, and I'm going to look at each one. So for probe 1, and this is the 1 to 10, so will divide the input voltage by 10. So if you remember, our amplitude of the triangle wave was originally 20. So when we divided it by 10, we get a max of 2. For this voltage division, it was 1 to 20. So 20 divided by 20, you have an amplitude of 1. And for divided by 5, 20 divided by 5, the amplitude is 4. And the same thing with probe 2. For probe 2, we divide by 10, and 20 divided by 10 is 2. And for 1 to 20, 20 divided by 20 is 1, and 20 divided by 5 is 4. Notice how the one probe is measuring this positive voltage, and the second probe is measuring this negative voltage. So now I need to, so if you look back at our circuit, that's all there is in this circuit file. That's because the rest of the oscilloscope is split up into different circuit files to decrease the simulation time and to break, and it makes it easier if you break it up into separate steps. So what we need to do now is we need to export. We need to export this data out and then input it back into the next circuit in the system. So in order to do that, we're first going to export it out as a text file. So and I'm going to name this text file analog probes because it's measuring the analog probe inputs. So I saved that as a text file. And now I'm going to go ahead and process some of that data in Excel. So here we are in Excel, and I'm going to open it up. I'm going to open it up right here. We'll find it, and there's our file. We open it up, and notice how this, when we export from TNet, it exports as a tab delimited text file. So everything's separated by tabs. So when I import back in and I tab delimit everything, I get the time and I get each of the probe inputs. Now, in order to import this back into the next TNet file, I need these all separated into separate text files. So in order to help me do that, I've developed a macro in Excel which will split these up for me. Now, macros can be found in the developer tab and enabled, but sometimes Excel doesn't have these settings open by default. So in order to enable macros, we can go down here to options. We'll need to first go to customize the ribbon, and you'll need to enable the developer tab. And then from here, you'll need to go to the trust center. You'll go to the trust center settings, and you may need to make sure that you enable the macros so you can actually run the macros. So with those two settings enabled, we should be good to go. So with this, we can go here and click macros. We see I developed 3 macros for this one. So for the first macro we're going to use is called split samples. And what that's going to do is just split these into separate files. So if I run this macro, see, we let it run, and it's splitting each one into its own separate file and stack. So if we want to look at how many samples our simulation pulled a total of about 397 samples. So that will be important later when we look at how, when running imported files from TNet, how things can change. So we're going to go ahead and save each individual one as a tab delimited file because TNet only reads imports and exports in tab delimited text files. So I'll save this one. I'll close it out. Then I'll save this one as a tab delimited. All right. This one, next one, save it as a tab delimited. Save that. And here's the next one. Tab delimited. Right, the next one, tab delimited. And I think this is the last one, tab delimited. Yep. Oh, never mind, one more. So tab delimited, save that. Okay, this is the original file. We can close that one out too. So now that I've exported them out as text files, I can import them back into the next TNet file as those tab delimited files.